Hello there. I'm so glad you found your way here tonight. Wherever you are in the world right now, allow yourself to settle into this shared moment of stillness. Let the noise of the day fade away. Let your thoughts grow quiet, like the gentle orbit of distant moons drifting around their planets. Right now, as you listen to these words, something extraordinary circles overhead. Hundreds of moons are spinning through the darkness of our solar system. Each one a world of its own, with secrets hidden beneath icy crusts and craters carved by ancient collisions. And somehow, from all that silent motion, you are here, listening, wondering. Tonight we journey outward, into the quiet realm of moons. A universe of frozen oceans, volcanic eruptions, and mysteries that have orbited for billions of years. We will explore how moons shape the tides of their planets, how some hide liquid water beneath their surfaces, how others erupt with geysers that spray ice crystals into space. All of it waiting to be shared in the stillness. Tonight, let's drift off together while exploring over 100 soothing facts about moons. There's no rush here. No test at the end. Just soft words and quiet wonders to carry you into rest. Welcome to Drowsy Discovery. I am glad you found your way here tonight. Perhaps you have had a long day. Perhaps you simply enjoy falling asleep to thoughts about the quiet companions that orbit our planets. Either way, this space is for you. There is something profoundly peaceful about contemplating moons. Every fact about these wandering worlds is a reminder that we are part of something far greater than ourselves. And they are always orbiting, always shifting, always carrying stories written in craters and ice. You are part of this story. The oxygen in your lungs was forged in ancient stars. The iron in your blood was born in supernova explosions that scattered across the cosmos. The atoms that make your cells have been part of nebulae, planets, and perhaps even moons that existed billions of years before you were born. If you enjoy these gentle journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here, too, one sleepy soul at a time. But for now, all you need to do is relax. So settle in, let your breathing slow, and let the weight of the day drift away, like moonlight fading into the cosmic background. Moons are patient beyond measure. They orbit for billions of years without haste. Craters form and remain unchanged for eons. Oceans stay hidden beneath ice, waiting to be discovered. And yet, within all that steadiness, there are sudden bursts of wonder. Volcanoes that erupt on Io, geysers that spray on Enceladus, tides that slowly reshape distant worlds. Tonight, we will wander through this magnificent realm of satellites. We will meet the moons that shape their planets and discover processes that determine the fate of countless worlds. And we will uncover truths about these cosmic companions that may surprise even the most curious minds. But there is no hurry. Moons have been orbiting for nearly 4.5 billion years. They can wait a little longer while you rest. Let us begin with our own faithful companion in the sky. Earth's moon is slowly drifting away from our planet. Every year, the moon moves approximately 3.8 centimeters farther from Earth, a distance roughly equivalent to the growth of a human fingernail. This gradual recession is caused by the transfer of angular momentum from Earth's rotation to the moon's orbit through tidal interactions. As the moon's gravity raises tides in Earth's oceans, friction between the water and the rotating Earth converts rotational energy into orbital energy, pushing the moon outward. Billions of years ago, the Moon was much closer to Earth, appearing dramatically larger in the sky and raising far more powerful tides. Over geological time, this outward drift will continue until the Moon reaches a stable distance, where it no longer gains energy from Earth's rotation. Eventually, both Earth and Moon will become tidally locked, each permanently facing the other with the same side. The Moon was born from a catastrophic planetary collision. Approximately 4.5 billion years ago, a Mars-sized protoplanet called Theia collided with the young Earth in one of the most violent events in our solar system's history. The impact was so powerful that it vaporized vast quantities of rock and ejected enormous amounts of molten material into orbit around our planet. This debris gradually coalesced under its own gravity over the following thousands of years, eventually forming the Moon we see today. Evidence for this giant impact hypothesis comes from the remarkable chemical similarity between lunar rocks and Earth's mantle, as well as the Moon's relatively small iron core. The collision likely tilted Earth's axis to its current inclination, setting the stage for our planet's seasons. Computer simulations suggest the impact occurred at a specific angle and velocity that allowed enough material to escape into orbit rather than falling back to Earth. The Moon once had an atmosphere of its own. In the distant past, when volcanic activity was still rampant on the lunar surface, the Moon possessed a thin atmosphere created by gases erupting from its interior. This ancient atmosphere, primarily composed of carbon monoxide, sulfur, and water vapor, was sustained by massive volcanic outpourings that occurred between 3 and 4 billion years ago. Studies of lunar rock samples brought back by Apollo astronauts revealed that volcanic eruptions were far more powerful than previously believed. However, the Moon's weak gravity, only about 1/6 of Earth's, meant it could not hold on to these gases for long. Over millions of years, solar winds stripped away the atmosphere, molecule by molecule, leaving the airless world we observe today. Without a protective magnetic field like Earth's, the Moon had no defense against the relentless bombardment of charged particles from the Sun. The far side of the Moon looks nothing like the side we see. While the near side of the Moon visible from Earth is marked by large dark plains called Maria, the far side is almost entirely covered with rugged highlands and countless impact craters. This striking asymmetry puzzled scientists for decades after the first images of the far side were returned by Soviet spacecraft in 1959. The dark Maria on the near side formed when ancient asteroid impacts punctured the thin crust, allowing molten lava to flood the basins. On the far side, the crust is significantly thicker, preventing lava from reaching the surface even after major impacts. This crustal asymmetry may have resulted from the Moon's early thermal evolution, when heat from Earth kept the near side warmer. The far side holds the largest and oldest impact basin in the solar system, the South Pole Aitken Basin, stretching over 2,000 kilometers across. The Moon once glowed with seas of molten lava. In its earliest epoch, immediately following the giant impact that created it, the Moon was covered by a global ocean of molten rock reaching depths of hundreds of kilometers. This magma ocean would have glowed brilliantly against the blackness of space, radiating heat at temperatures exceeding 1,000 degrees Celsius. As this ocean slowly cooled over millions of years, lighter minerals floated to the top and crystallized to form the bright highlands we see today. The process of cooling and crystallization took between 10 and 200 million years. Later volcanic activity produced new lava flows that filled the giant impact basins, creating the dark Maria visible from Earth. These volcanic eruptions continued sporadically for over 1 billion years, with some evidence suggesting minor volcanic activity may have occurred as recently as 100 million years ago. The moon reflects only 12% of the sunlight that hits it. Despite appearing brilliantly white in the night sky, the moon is actually one of the darkest objects in the solar system, with a reflectivity similar to worn asphalt or coal. This property, called albedo, measures how much light a surface reflects rather than absorbs. The lunar surface is covered with a dark gray powder called regolith, composed of pulverized rock, glass beads and mineral fragments, created by billions of years of meteorite bombardment. The reason the moon appears so bright is simply because there is nothing else in the night sky to compare it to, and our eyes adjust to see it as luminous. Fresh impact craters expose brighter material from beneath the surface, creating the rays that extend outward from young craters like Tycho. If you place the moon next to Saturn's moon Enceladus, which reflects nearly all sunlight, our moon would look almost black by comparison. Without the moon, life on Earth might never have evolved. The moon has played a crucial role in making Earth hospitable for complex life through several interconnected mechanisms over billions of years. The tidal forces generated by the moon create rhythmic movements of ocean waters that may have helped concentrate the chemicals necessary for the origin of life. These tides continue to drive mixing in the oceans, distributing nutrients and oxygen in ways that support marine ecosystems. Perhaps most importantly, the moon stabilizes Earth's axial tilt at roughly 23.5 degrees, preventing chaotic oscillations that would cause extreme climate swings. Without this gravitational anchor, Earth's tilt could vary wildly, alternately baking and freezing each hemisphere. The moon also slowed Earth's rotation from an initial period of just a few hours to our current 24-hour day. The moon helps keep Earth's axis stable. Earth's axial tilt of approximately 23.5 degrees is the reason we experience seasons, with each hemisphere alternately tilted toward or away from the sun throughout the year. The gravitational influence of the moon acts as a stabilizing force that prevents this tilt from changing dramatically over millions of years. Computer simulations have shown that without the moon, gravitational tugs from the sun and other planets would cause Earth's axis to wobble chaotically. Such extreme variations would cause catastrophic climate changes, with tropical regions experiencing polar conditions within relatively short timeframes. Mars, which lacks a large moon, has experienced exactly this kind of axial wandering over millions of years. The moon's gravitational anchor keeps Earth's seasons predictable and relatively mild. The moon makes our days longer over time. The same tidal forces that push the moon away from Earth also slow our planet's rotation, gradually lengthening the day by approximately 2 milliseconds every century. This may seem insignificant, but accumulated over billions of years, the effect has been profound. When the moon first formed, a day lasted only about 6 hours. Ancient coral fossils preserve daily growth rings that confirm Earth's days have been steadily lengthening throughout geological history. Approximately 600 million years ago, studies indicate that a day was only about 21 hours long, and a year contained over 400 days. The mechanism behind this slowing is the friction between ocean tides and the seafloor. This cosmic braking system will continue to slow Earth's rotation until eventually both Earth and Moon become tidally locked. The Moon's gravity makes Earth slightly egg-shaped. While we often picture Earth as a perfect sphere, the combined gravitational pull of the Moon and Sun actually distorts our planet into a slightly elongated shape. This tidal bulge in the solid rock of Earth is subtle, raising the surface by just a few centimeters, but the effect on the oceans is far more pronounced. The side of Earth facing the Moon experiences a stronger gravitational pull than the center, creating a bulge toward the Moon, while the opposite side bulges away because it feels a weaker pull. This double bulge is why most coastal regions experience 2 high tides and 2 low tides each day. The Moon's gravitational influence also affects the atmosphere, creating atmospheric tides that subtly influence weather patterns. Even the solid ground beneath your feet rises and falls by about 30 centimeters during the course of a day. The Moon helps trigger earthquakes and volcanic shifts on Earth. While earthquakes are primarily caused by the movement of tectonic plates, the Moon's gravitational pull can act as a trigger for seismic events in areas already under geological stress. Studies have found correlations between tidal forces and the timing of some large earthquakes, particularly in subduction zones. The additional stress from high tides, though small, can be enough to tip an already strained fault zone over the threshold into rupture. Research has shown a slight tendency for major seismic events to occur during periods of especially strong tidal forces, such as during full and new moons. Volcanic activity also appears to respond to tidal forces, with some volcanoes showing increased activity during certain phases of the lunar cycle. The mechanism involves the subtle squeezing and stretching of magma chambers and the crust above them. The Moon still trembles with mysterious moonquakes. Despite being considered geologically dead for billions of years, the Moon continues to experience seismic activity detected by instruments left behind by Apollo astronauts. These moonquakes come in 4 distinct types: deep moonquakes occurring about 700 kilometers below the surface, shallow moonquakes closer to the surface, thermal moonquakes caused by temperature changes, and impact-related quakes. The deep moonquakes follow a regular pattern tied to the Moon's orbital position, suggesting they are triggered by Earth's gravitational pull. Shallow moonquakes are the most powerful and mysterious, sometimes reaching magnitudes of over 5 on the Richter scale. Unlike earthquakes that typically last seconds to minutes, moonquakes can last for hours, as seismic waves bounce around the rigid lunar interior. Some of these shallow tremors appear to originate from the same locations, hinting at ancient fault systems. Tiny glass beads on the Moon hide trapped water. Scattered across the lunar surface are billions of tiny glass spheres, formed when volcanic eruptions or meteorite impacts melted rock and launched droplets that cooled rapidly into glass. Analysis of these glass beads brought back by Apollo missions and the Chinese Chang'e 5 mission revealed that many contain water molecules trapped within their internal structure. The water likely originated from solar wind hydrogen interacting with oxygen in the lunar soil, or from the Moon's ancient volcanic activity. Scientists estimate that these glass beads could collectively contain substantial amounts of water, potentially making them a valuable resource for future lunar explorers. The water can be released by heating the glass beads, providing a potential extraction method for astronauts. This discovery has transformed our understanding of the lunar surface, from a completely dry wasteland to a world containing hidden reservoirs. The Moon is covered in dust that smells like burnt gunpowder. Apollo astronauts who walked on the Moon reported that the lunar dust clinging to their suits had a distinctive odor once they returned to their spacecraft, variously described as burnt gunpowder, spent fireworks, or wet ashes. This peculiar smell was noticeable immediately after removing their helmets inside the lunar module, though it faded as the dust became oxidized. The lunar regolith is an extremely fine powder with sharp, jagged edges because there is no wind or water on the Moon to smooth the particles as happens on Earth. These microscopic glass shards and mineral fragments proved highly abrasive, wearing through spacesuit material and coating every surface with clinging gray powder. The dust posed unexpected challenges during the Apollo missions, jamming equipment and scratching helmet visors. Scientists believe the smell may result from silicon dioxide particles reacting with moisture in the astronauts' nasal passages. Lunar soil cuts through spacesuit fabric like glass. The lunar regolith is far more dangerous than ordinary dust, composed of tiny particles with razor-sharp edges that never become rounded, because there is no erosion process on the airless moon. Billions of years of micrometeorite bombardment have pulverized the surface into a powder of jagged glass shards and mineral fragments that shred materials on contact. During the Apollo missions, astronauts found that their suit fabrics wore through at an alarming rate. The same abrasive quality caused problems with seals and moving parts, jamming zippers, and degrading equipment performance. Laboratory studies have shown that lunar dust particles can cut through protective fabrics and damage lung tissue if inhaled. The electrical charge that lunar dust carries causes it to cling stubbornly to any surface. Designing spacesuits for long-duration lunar missions remains a significant engineering challenge. The Moon holds frozen water in permanently shadowed craters. Deep within craters near the lunar poles, regions exist that have never seen sunlight for billions of years, remaining in permanent shadow cast by the crater rims. These eternally dark areas are among the coldest places in the solar system, with temperatures plunging below -200 degrees Celsius. Spacecraft observations have confirmed the presence of water ice in these shadowed craters, likely delivered by comet impacts over eons. The distribution of ice appears patchy, with some craters containing substantial deposits, while others remain relatively dry. This water ice represents an invaluable resource for future lunar exploration, potentially providing drinking water, oxygen for breathing, and hydrogen for rocket fuel. Technologies using reflected sunlight or nuclear power sources are being developed to enable extraction of this frozen treasure. A moon rings like a bell after quakes. When the Apollo astronauts deliberately crashed rocket stages onto the moon's surface, the seismometers they had left behind recorded something extraordinary. The moon rang like a bell for hours after each impact. This prolonged reverberation occurs because the lunar surface is extremely dry and fractured, allowing seismic waves to bounce around repeatedly. The longest recorded moonquake reverberation lasted over an hour, with the seismic signals slowly fading rather than stopping abruptly. This phenomenon revealed important information about the moon's internal structure, indicating a rigid, dry crust extensively fractured by billions of years of impacts. The absence of water in lunar rocks means there is nothing to dampen vibrations. Scientists have used this ringing behavior to map the moon's interior, much as geologists use earthquake waves to study Earth's hidden layers. Astronaut footprints on the moon will last for millions of years. The bootprints left by Apollo astronauts in the lunar soil will remain virtually unchanged for millions of years, because there is no wind, rain, or geological activity to erase them on the airless moon. On Earth, footprints in sand disappear within hours due to weather, but the moon's surface is frozen in time. The only forces that can alter these prints are micrometeorite impacts and the solar wind that very gradually erodes exposed particles. Scientists estimate it will take between 10 and 100 million years for natural processes to completely obliterate the human tracks. Alongside the footprints, the rovers, wheel tracks and equipment marks remain exactly as they were decades ago. These first human footsteps on another world have become monuments, marking humanity's initial steps into the cosmos. Astronauts left experiments that are still running today. Among the most enduring legacies of the Apollo missions are the retroreflector arrays left on the lunar surface, which remain operational more than 50 years after deployment. These panels of special corner cube reflectors bounce laser beams directly back toward their source on Earth, allowing scientists to measure the Earth-Moon distance with extraordinary precision. Ongoing laser ranging experiments have tracked the Moon's gradual recession from Earth, tested Einstein's theory of general relativity, and revealed subtle orbital variations. The measurements achieve accuracies of just a few centimeters across 384,000 kilometers. 2 American retroreflectors were placed by Apollo 11 and 14, while a third larger array was deployed by Apollo 15. The Soviet Union also landed 2 retroreflectors carried by robotic Lunokhod rovers. The Moon holds the record for the coldest known places in the solar system. Measurements from the Lunar Reconnaissance Orbiter have detected temperatures in permanently shadowed craters near the Moon's south pole, reaching as low as -248 degrees Celsius, colder than any surface temperature measured elsewhere. These extreme temperatures exist because the crater floors have been in perpetual shadow for billions of years, never receiving direct sunlight. Even Pluto has a warmer surface temperature because its thin atmosphere provides some insulation. The coldest spots occur in small depressions within larger craters, where even scattered light cannot reach. At these temperatures, water, carbon dioxide, and other volatiles remain frozen solid. These ultra-cold regions may preserve ancient molecules delivered by comets, creating a frozen record of solar system chemistry. The Moon once glowed red during ancient eclipses. During total lunar eclipses, the Moon takes on a reddish or coppery hue because Earth's atmosphere bends sunlight around our planet's edge and filters out shorter wavelengths. This same effect that makes sunsets red on Earth paints the Moon during eclipses, creating what is sometimes called a blood moon. Ancient civilizations interpreted these red moons as omens or signs from their gods. The exact color depends on atmospheric conditions on Earth, with dusty atmospheres producing darker eclipses. Major volcanic eruptions that inject aerosols into the upper atmosphere can dramatically darken subsequent eclipses. Historical records of eclipse colors have been used to track volcanic activity throughout human history. Europa's hidden ocean may contain more water than Earth. Beneath the icy crust of Jupiter's moon, Europa lies a global ocean that scientists estimate may contain 2 to 3 times more liquid water than all of Earth's oceans combined. This vast subsurface sea is kept liquid by tidal heating, as Jupiter's immense gravity flexes Europa's interior during its elliptical orbit. The ocean is thought to extend to depths of 100 kilometers or more, sandwiched between an outer ice shell and a rocky seafloor. Evidence comes from the Moon's induced magnetic field and surface features suggesting the ice floats on liquid. The water may have been in contact with rock for billions of years, allowing enrichment with minerals necessary for life. Future missions aim to study this ocean by analyzing material ejected from the surface. Europa's ice surface constantly reshapes itself. The surface of Europa is remarkably young in geological terms, estimated at only about 40 to 90 million years old based on the scarcity of impact craters. This youthful appearance suggests that material from the subsurface ocean rises to create new surface ice, while older ice is recycled back into the interior. The surface is crisscrossed by thousands of linear features called lineae, dark bands that can stretch for thousands of kilometers. Scientists believe these bands form when the ice shell cracks due to tidal flexing, and warmer material wells up from below to fill the gaps before freezing. Some regions show chaotic terrain where large blocks of ice appear to have broken apart and refrozen. There is evidence of plate tectonics-like activity, with ice plates spreading apart in some regions. Europa may harbor hydrothermal vents like Earth's oceans. If Europa's rocky interior is heated by tidal forces, there is a strong possibility that hydrothermal vents exist on the floor of its subsurface ocean, similar to the black smokers and white smokers found in Earth's deep oceans. On Earth, these volcanic vents support thriving ecosystems of microbes, tubeworms, and other organisms that derive energy from chemical reactions rather than sunlight, demonstrating that life can flourish without any connection to the sun. The discovery that Earth's seafloor vents host such diverse life revolutionized our understanding of where life can exist, and immediately raised the possibility that similar oases might exist elsewhere. Europa's ocean has been in contact with rock for billions of years, potentially leaching minerals and nutrients that could support chemosynthetic life forms. The combination of liquid water, chemical energy from rock-water interactions, and organic compounds delivered by comets creates conditions that many scientists consider ideal for the emergence of simple life. Missions are being designed to search for biosignatures in material ejected from Europa's surface, and ultimately to probe the ocean directly. If life exists in Europa's dark ocean, it would represent an independent origin of life, perhaps the most profound discovery in human history. Life could potentially emerge on Europa. Europa possesses the three key ingredients scientists believe are necessary for life: liquid water, a source of chemical energy, and the organic building blocks that form biological molecules. The Moon's subsurface ocean has existed for billions of years, potentially providing a stable environment where evolution could have had ample time. Unlike the harsh surface environment exposed to Jupiter's intense radiation, the deep ocean beneath kilometers of protective ice would be shielded. Chemical energy could come from hydrothermal vents on the seafloor, or from oxidants produced by radiation at the surface. Organic molecules are likely present, delivered by the constant rain of comets and asteroids. Whether life has actually emerged on any moon remains unknown, but conditions appear favorable enough that missions are being planned to search for biosignatures. Europa's smooth surface hints at a restless world beneath. Among all the solid bodies in the solar system, Europa has one of the smoothest surfaces, with few large mountains or deep valleys, and an appearance that resembles cracked eggshell. This smoothness results from the relative youth of the ice surface, which is continuously renewed by processes driven by the Moon's internal heat. The comparative lack of large impact craters tells astronomers that the surface we see today has been resurfaced since the intense bombardment billions of years ago. The gentle topography also suggests that the ice shell may be relatively thin in some regions. Various resurfacing mechanisms have been proposed, including complete overturning of the ice shell, gradual rising of warm ice from below, and localized melting events. Europa's bland exterior conceals one of the most dynamic geological environments in the outer solar system. Enceladus erupts geysers that shoot into space. From fractures in the south polar region of Saturn's tiny moon Enceladus, spectacular plumes of water vapor and ice particles blast continuously into space, shooting material hundreds of kilometers above the surface. These geysers were discovered by the Cassini spacecraft in 2005, revealing remarkable geological activity on this world only 500 kilometers across. The plumes contain not just water but also complex organic molecules, silica particles suggesting hydrothermal activity, and salts indicating a subsurface ocean. The volume of material ejected is substantial enough that Enceladus creates Saturn's diffuse E-ring. The plumes emerge from a network of parallel fractures nicknamed tiger stripes. Cassini flew through these plumes multiple times, confirming the presence of molecular hydrogen, a potential food source for microbes. Enceladus, geysers feed Saturn's rings. The ice particles erupted from Enceladus, south polar geysers form the raw material for Saturn's E-ring, one of the planet's largest and most diffuse rings extending from the orbit of Mimas outward. particles ejected at speeds exceeding the Moon's escape velocity drift into orbits around Saturn. The E-ring is visually faint because it consists of tiny particles less than a micrometer in diameter. Fresh material is constantly being supplied by Enceladus, replacing particles lost through various processes. Scientists estimate that Enceladus supplies several hundred kilograms of ice per second to the E-ring. The E-ring's composition provided early clues that led researchers to propose a liquid water source within Enceladus, even before the plumes were observed. Enceladus' south pole is a landscape of tiger stripes. The south polar region of Enceladus is dominated by 4 parallel fractures, each about 130 kilometers long, that have been nicknamed tiger stripes. These fractures are the sources of the geyser activity that makes Enceladus so fascinating. Infrared observations reveal that the tiger stripes are significantly warmer than the surrounding terrain. The warmth comes from tidal flexing as Enceladus orbits Saturn in an elliptical path. Along each tiger stripe, jets of water vapor and ice particles erupt from specific points where the underlying ocean is closest to the surface. The entire south polar region is geologically young, with few impact craters. Enceladus is one of the brightest objects in the solar system. Enceladus reflects nearly all of the sunlight that strikes its surface, giving it an albedo of approximately 99%, making it one of the most reflective objects in our solar system. This extreme brightness results from the Moon's surface being constantly coated with fresh snow falling from its own geysers. Most of the ice ejected by the south polar plumes falls back as fine powder, covering Enceladus in pristine frost. The freshness of this coating means there has been little time for space weathering to darken the surface. By comparison, our Moon reflects only about 12% of sunlight. This brilliant whiteness is a direct visual signature of the Moon's active geology. Enceladus may contain the building blocks of life. When the Cassini spacecraft flew through the plumes erupting from Enceladus, its instruments detected a rich cocktail of organic molecules, including complex compounds far larger than simple organics, like methane. The detection of these complex organics suggests that sophisticated chemistry is occurring within the subsurface ocean. Cassini also found molecular hydrogen in the plumes, which could be produced by hydrothermal reactions between hot water and rock. Silica nanoparticles indicate that water temperatures at the ocean floor may reach 150 degrees Celsius or higher. The combination of liquid water, organic compounds, chemical energy, and the right physical conditions makes Enceladus one of the most promising places to search for life beyond Earth. Titan has lakes and seas of liquid methane. Saturn's largest moon, Titan, is the only world besides Earth known to have stable bodies of liquid on its surface, but instead of water, these are filled with liquid methane and ethane. These hydrocarbon seas are concentrated near the North Pole, where Ligeia Mare and Kraken Mare cover thousands of square kilometers. The lakes appear dark in radar images because the smooth liquid surface reflects radar waves away. Kraken Mare is comparable in size to Earth's Caspian Sea and reaches depths of several hundred meters. The liquid hydrocarbons exist because Titan's surface temperature hovers around -179 degrees Celsius. Unlike Earth's water cycle, Titan has a methane cycle with evaporation, clouds, and rain. Titan has an atmosphere thicker than Earth's. Unlike nearly all other moons in the solar system, Titan possesses a dense atmosphere with a surface pressure about 50% greater than Earth's. This thick atmosphere is primarily composed of nitrogen, much like Earth's, with about 5% methane and smaller amounts of other hydrocarbons. The atmosphere extends far higher than Earth's relative to the Moon's size, forming a puffy envelope that obscures the surface with thick orange haze. This haze is composed of tholins, complex organic molecules produced when ultraviolet light breaks down methane in the upper atmosphere. The cold temperature helps slow molecular velocities enough to retain the atmosphere, while volcanic outgassing may continuously replenish losses. Titan's thick atmosphere creates a greenhouse effect that moderates surface temperatures. Titan's orange haze may resemble early Earth's atmosphere. The thick orange smog that shrouds Titan is often compared to what Earth's atmosphere might have looked like billions of years ago, before life oxygenated our planet. This haze is produced by photochemistry in the upper atmosphere, where solar ultraviolet radiation breaks apart methane molecules and initiates reactions building complex organic compounds. Some scientists believe studying Titan provides a natural laboratory for understanding the prebiotic chemistry that may have given rise to life on early Earth. The tholins produced eventually settle onto the surface, coating the landscape with organic material. Laboratory experiments recreating Titan's atmospheric chemistry have produced amino acids and nucleotide bases. Titan serves as a frozen snapshot of the organic chemical evolution that may have preceded life on our own world. Titan has mountains taller than the Rockies made of ice. The surface of Titan features mountain ranges reaching heights of around 3,000 meters, composed not of rock but of water ice, which at Titan's frigid temperatures is as hard as granite on Earth. These icy peaks were revealed by the Cassini spacecraft's radar instruments, which could penetrate the thick atmospheric haze. The mountains appear to be relatively old features, worn down by the slow erosion of methane rain and wind-blown organic particles. Their heights are modest compared to the tallest mountains on Earth, but still impressive on a world where ice plays the role of rock. The mountains may have formed through tectonic processes or through cryovolcanism. Walking among these frozen peaks would be a surreal experience, with orange skies and methane rivers carving valleys through cliffs of water ice. Titan has rivers and rain of liquid methane. On Titan, methane plays the role that water plays on Earth, existing as a gas in the atmosphere, falling as rain, and flowing across the surface in rivers that carve channels. The Huygens probe captured images of drainage channels carved by flowing liquid that looked remarkably similar to river valleys on Earth. These methane rivers flow from highlands toward the polar seas, cutting through the organic-coated ice. Rain falls relatively rarely on Titan, with intervals of years to decades between storms, but when precipitation does occur, it can be intense. The low gravity and dense atmosphere mean raindrops fall slowly and can grow quite large. Flash floods may occasionally rage through dry channels, reshaping the landscape in sudden bursts of activity. Io's explosive volcanoes outshine anything on Earth. Jupiter's moon Io hosts the most violent volcanic activity in the known solar system, with eruptions that dwarf anything witnessed on Earth both in scale and frequency. Some eruptions produce fountains of lava, shooting hundreds of kilometers above the surface. The volcanic hotspots can reach temperatures exceeding 1700 degrees Celsius. This extreme volcanism is powered by tidal heating, as Jupiter's gravity continuously squeezes Io's interior during its elliptical orbit. The Moon is locked in an orbital resonance with Europa and Ganymede that keeps its orbit slightly elliptical. Roughly 400 active volcanic centers have been identified on Io's surface. Io's lava flows can stretch for hundreds of miles. The volcanic eruptions on Io produce rivers of molten silicate rock that can flow for hundreds of kilometers across the Moon's surface. These lava channels are among the longest ever observed on any planetary body. The flows spread so far because of the extremely high temperatures and low viscosity of Io's lavas, combined with the Moon's lower gravity. Some flows have been observed to change dramatically between successive spacecraft visits. The longest individual lava flow observed on Io stretches over 500 kilometers. These rivers of fire reshape Io's surface on timescales of years to decades. Io is the most volcanically active world in the solar system. With approximately 400 active volcanic centers scattered across its surface, Io erupts more frequently and intensely than any other body ever studied. The Moon's entire surface is composed of recently erupted volcanic materials, with essentially no impact craters visible. Io's volcanic output is so prolific that the entire surface is resurfaced to a depth of several meters every million years. The distinctive yellow, orange, red and black colors come from different forms of sulfur and silicate lavas. Sulfur dioxide ejected by eruptions creates a thin atmosphere that freezes onto the surface during night. This continuous outgassing feeds a torus of ionized particles that encircles Jupiter. Io's surface is constantly being reshaped by eruptions. The volcanic activity on Io is so intense that the surface changes noticeably between observations, separated by only weeks or months. Scientists comparing images from Voyager in 1979 with those from Galileo in the late 1990s found dramatic transformations. Mountains on Io can rise rapidly through tectonic forces, sometimes reaching heights of over 17 kilometers. These mountains often tilt and slide as their foundations are undermined by continued volcanic activity. The constant resurfacing means that Io has no preserved impact craters. Io is a world in perpetual geological chaos. Io's volcanoes are powered by tidal forces from Jupiter. The extraordinary volcanic activity on Io is not driven by radioactive decay, but by the gravitational tug-of-war between Jupiter and Io's neighboring moons Europa and Ganymede. These three moons are locked in an orbital resonance that keeps Io's orbit slightly elliptical. This elliptical orbit means Io's distance from Jupiter varies, and Jupiter's enormous gravity stretches and compresses the Moon's interior. This continuous flexing generates friction within Io's rocky interior, maintaining a global magma ocean beneath the solid crust. Computer models suggest that tidal heating produces about 200 trillion watts of power continuously. Io demonstrates that worlds far from the Sun can maintain active geology through gravitational interactions alone. Ganymede is the largest moon in the solar system. With a diameter of 5,268 kilometers, Ganymede exceeds even the planet Mercury in size, though it contains less than half Mercury's mass due to its composition of rock and ice. This giant moon orbits Jupiter at a distance of just over 1 million kilometers, completing one circuit every 7 Earth days in a tidally locked configuration. The Moon is composed of roughly equal amounts of silicate rock and water ice, giving it a layered internal structure. Surface features include ancient, heavily cratered dark regions, and younger, brighter terrain crisscrossed by grooves and ridges. Ganymede has been known since Galileo first observed it in 1610. This massive moon dominates Jupiter's satellite system. Ganymede has its own magnetic field. Ganymede is the only moon in the solar system known to generate its own magnetic field through an internal dynamo, just as Earth does with its spinning liquid iron core. This intrinsic magnetosphere is embedded within Jupiter's much larger magnetic field, creating a unique magnetic environment. The existence of this magnetic field implies that Ganymede's iron core must be at least partially liquid and convecting. Aurora have been observed on Ganymede, caused by charged particles interacting with the Moon's thin oxygen atmosphere. Measurements of how Ganymede's magnetic field wobbles provided some of the first evidence that a salty ocean exists beneath the surface. This hidden ocean may be about 100 kilometers thick and 10 times deeper than Earth's oceans. Ganymede's crust is layered like a cosmic sandwich. The interior of Ganymede is structured in distinct layers that resemble a cosmic sandwich. At the center lies an iron-rich core, possibly partially molten, surrounded by a rocky mantle. Above this sits a layer of high-pressure ice, followed by a liquid ocean of salty water. Topping this ocean is another layer of ice that creates the visible surface features. Scientists believe there may actually be multiple ocean layers sandwiched between different phases of ice. This complex layering has implications for the habitability of the ocean. Ganymede's layered structure is a natural laboratory for studying planetary body differentiation. Ganymede is larger than the planet Mercury. In the hierarchy of solar system sizes, Ganymede occupies a unique position as a moon larger than the smallest planet. However, Mercury is significantly denser, consisting primarily of metal and rock, giving Mercury about twice Ganymede's mass despite its smaller volume. This size comparison highlights the somewhat arbitrary distinction between planets and moons. Ganymede's surface gravity is only about 14% of Earth's, less than half of Mercury's. If Ganymede were transported to an independent orbit around the Sun, it would qualify as a planet. Ganymede demonstrates that size alone does not determine classification. Ganymede may hide multiple stacked oceans beneath its surface. Models of Ganymede's internal structure suggest that rather than a single subsurface ocean, there may be several layers of liquid water sandwiched between different phases of ice at various depths. The immense pressure deep within this large moon causes water ice to transform into exotic high-pressure phases with different crystal structures. A liquid ocean could exist between each of these ice phases wherever conditions are right. The uppermost ocean would lie beneath the surface ice shell, at depths of perhaps 150 kilometers. This stacking occurs because different ice phases have different densities, allowing liquid water to be buoyant against some phases while dense against others. The implications for habitability are significant, as organic materials might only reach the uppermost ocean. Callisto may hold an ancient ocean beneath its crust. Magnetic field measurements from the Galileo spacecraft suggest that Callisto harbors a liquid ocean beneath its heavily cratered surface. The evidence comes from the way Jupiter's magnetic field induces electrical currents in Callisto, indicating a salty, electrically conducting layer. This presumed ocean would lie at depths of perhaps 100 or more kilometers, kept liquid by residual internal heat and possibly antifreeze compounds. Unlike Europa and Ganymede, Callisto shows no signs of past geological activity on its surface. The ocean on Callisto may be one of the oldest unchanged environments in the solar system. Callisto's distance from Jupiter reduces radiation bombardment compared to the inner Galilean moons. Callisto's ancient craters may be 4 billion years old. The surface of Callisto is so heavily cratered that scientists believe it preserves an impact record dating back to the earliest days of the solar system. Unlike the other Galilean moons, Callisto shows no evidence of geological resurfacing that would erase ancient craters. This makes Callisto's surface one of the oldest, relatively unchanged landscapes in the solar system. The largest impact structure, Valhalla, consists of a bright central zone roughly 600 kilometers across, surrounded by concentric rings. These multi-ringed basins formed when the icy crust was more plastic, allowing impact shock waves to create rippling patterns. Callisto is essentially a museum of the ancient solar system. Callisto is one of the most heavily cratered objects in the solar system, with virtually every square kilometer of its surface pockmarked by overlapping impact craters of all sizes. Callisto represents one of the most battered surfaces ever observed. The saturation of craters is so complete that new impacts can only create features by obliterating existing ones. This extreme cratering density indicates that Callisto's surface has remained essentially unchanged for over 4 billion years. The craters range from tiny pits to massive multi-ringed basins hundreds of kilometers across. Some of the oldest craters have been softened by slow, viscous relaxation of the ice. Callisto's cratered face tells the story of a geologically dead world, simply accumulating cosmic scars. Callisto is a frozen time capsule of the early solar system. Among all the large moons of the outer solar system, Callisto is unique in appearing to preserve conditions from the earliest days of planetary formation. While Europa's surface is perhaps only 50 million years old, and Ganymede shows evidence of past activity, Callisto's surface appears to date back over 3.8 billion years. The Moon never fully differentiated into distinct layers, with its ice and rock remaining partially mixed. This incomplete differentiation suggests that Callisto formed more slowly or at lower temperatures than the inner Galilean moons. Scientists studying the early solar system turned to Callisto as a reference point for understanding primordial conditions. Callisto stands as a frozen witness to the birth of the planets. Triton orbits Neptune backwards. Unlike almost all large moons in the solar system, Triton orbits Neptune in a retrograde direction, moving clockwise when viewed from above Neptune's north pole, while the planet rotates counterclockwise. This backwards orbit strongly suggests that Triton was captured from the Kuiper Belt after wandering too close to the ice giant. The capture process would have been catastrophic, requiring Triton to lose enormous amounts of energy. Before being captured, Triton was likely a large Kuiper Belt object similar to Pluto. The capture event probably destroyed or ejected whatever moons Neptune originally possessed. Triton's retrograde orbit is slowly decaying, meaning the Moon is gradually spiraling inward toward eventual destruction. Triton may have been captured from the Kuiper Belt. The evidence for Triton's captured origin is compelling, based on its retrograde orbit, its Pluto-like size and composition, and computer simulations showing that such captures are possible. Triton's diameter of 2,700 kilometers makes it comparable to Pluto, and its surface composition matches what we observe on Kuiper Belt objects. The mechanism of capture remains debated, with possibilities including collision with an original Neptune moon, or interactions with a gaseous disk around young Neptune. If Triton was a Kuiper Belt object, it provides a unique opportunity to study such a body up close. The capture event would have generated enormous tidal heating, as Triton's initially eccentric orbit was circularized. Triton is a visitor from the frozen frontier, permanently detained by Neptune's gravity. Triton's surface is made of nitrogen ice. The surface of Triton is covered primarily with frozen nitrogen, along with smaller amounts of carbon monoxide and carbon dioxide ice. At temperatures around -235 degrees Celsius, nitrogen exists as a solid that exhibits seasonal sublimation patterns. The nitrogen ice creates a highly reflective surface that gives Triton an albedo of over 70%. Voyager 2 revealed a young-looking surface with relatively few craters. The nitrogen ice appears to flow slowly like glaciers on Earth, filling in low areas and creating smooth plains. Some regions show a distinctive cantaloupe texture that may result from convection within the nitrogen ice. Triton has geysers that vent nitrogen gas. When Voyager 2 flew past Triton in 1989, it discovered active geysers erupting dark material several kilometers above the frozen surface. These geysers are powered by the sun's warming of dark patches beneath the translucent nitrogen ice, which heats enclosed nitrogen until it vaporizes and erupts. The dark streak patterns visible extending for hundreds of kilometers from geyser sites are deposits of material carried aloft and blown by the thin atmosphere. The geysers produce plumes that rise to about 8 kilometers before being bent horizontal by atmospheric winds. This cryovolcanic activity demonstrates that even at temperatures just 38 degrees above absolute zero, geological processes continue. Triton's geysers show that active worlds exist even at the frigid boundaries of our solar system. Triton may one day break apart into a ring around Neptune. Triton's retrograde orbit causes tidal interactions that transfer angular momentum in the opposite direction from the common case, causing the orbit to slowly shrink rather than expand. Over the next few billion years, this orbital decay will bring Triton ever closer to Neptune until it crosses the Roche limit, where tidal forces exceed the Moon's internal gravity. When this happens, Triton will be stretched and shattered into countless fragments, forming a magnificent ring system. Scientists estimate this destruction will occur in approximately 3.6 billion years. The resulting ring system may be temporary on cosmic timescales, as particles gradually fall into Neptune or are swept up by remaining moons. Triton's future transformation represents one of the most dramatic fates awaiting any moon in our solar system. Iapetus has a mysterious dark hemisphere. Saturn's moon Iapetus displays one of the most striking color contrasts in the solar system, with one hemisphere as dark as charcoal and the other as bright as snow. The leading hemisphere is covered in dark material with an albedo of only 4%, while the trailing hemisphere reflects up to 60% of incoming sunlight. Scientists proposed that dark dust from the outer moon Phoebe spirals inward and is swept up by Iapetus' leading face. Once deposited, the dark material absorbs more sunlight and warms slightly, causing underlying ice to sublimate and migrate to colder regions. The dark coating is only a few meters thick at most, overlying bright water ice. Iapetus wears a mask on one face, darkened by the dust of a distant neighbor. Hyperion spins through space like a tumbling sponge. Unlike virtually every other substantial moon, Hyperion does not rotate smoothly on a fixed axis, but instead tumbles chaotically through space. This erratic rotation results from Hyperion's irregular shape and its orbital resonance with Titan. The moon's surface resembles a sponge or piece of coral, covered with deep, sharp-edged craters. Some craters are so deep that their dark floors lie far below the average surface level. Hyperion's low density suggests it may be a loosely consolidated rubble pile rather than a solid body. The dark material filling the crater floors may be similar to the dark coating on Iapetus. Hyperion's chaotic tumble makes it unique among moons large enough to be imaged in detail. Pan looks like a cosmic ravioli. Saturn's tiny moon Pan orbits within the Encke gap in Saturn's A-ring, and its peculiar flattened shape, with a prominent equatorial ridge, makes it look remarkably like a piece of ravioli pasta. The ridge formed as ring particles accumulated around Pan's equator over millions of years. Pan's diameter is only about 35 kilometers at its widest point. The moon acts as a shepherd, gravitationally clearing the Encke gap and preventing ring particles from diffusing into this region. Similar ridged shapes have been found on other small moons embedded within or near Saturn's rings. Pan and its ravioli-shaped companions are sculptured by their environment, shaped by the very rings they help maintain. Mimas looks strikingly like the Death Star. Saturn's moon Mimas features a giant impact crater named Herschel that spans nearly 1/3 of the moon's entire diameter, giving Mimas an uncanny resemblance to the fictional Death Star from Star Wars films. The crater is 130 kilometers across, with walls 5 kilometers high and a central peak rising nearly 6 kilometers. Scientists calculate that a slightly larger or faster impactor would have broken Mimas into pieces. The coincidental resemblance to the Death Star was noted soon after Voyager 1 returned the first detailed images in 1980. Herschel crater dominates one hemisphere of this frozen world, a permanent reminder of a violent ancient encounter. Recent discoveries suggest this Death Star lookalike may harbor surprising secrets. Mimas may hide a liquid ocean beneath its icy crust. Despite its small size and ancient, heavily cratered surface, recent analysis of Mimas' orbital motion has revealed unexpected oscillations that strongly suggest a liquid ocean beneath the ice. The way Mimas wobbles as it orbits Saturn can only be explained if the icy shell is decoupled from its rocky interior by liquid water. This discovery came as a complete surprise, as Mimas was considered the least likely to harbor an ocean. If the ocean exists, it must be relatively young, perhaps only about 25 million years old. Mimas joins Enceladus as an ocean world in the Saturn system, but one with no surface evidence of its secrets. This unexpected discovery reminds scientists that ocean worlds may be more common than previously suspected. Phobos is slowly spiraling toward its doom. The larger of Mars' two tiny moons, Phobos, orbits so close to its planet that it circles Mars 3 times every Martian day. This close orbit is unstable because tidal interactions with Mars are causing Phobos to spiral inward at about 1.8 meters per century. In approximately 50 million years, Phobos will either crash into Mars or be torn apart by tidal forces, creating a temporary ring around the red planet. Phobos already shows signs of stress, with long grooves that may be fractures caused by increasing tidal forces. The Moon measures only about 22 kilometers across and is irregularly shaped. Phobos is living on borrowed time, a doomed satellite counting down the millions of years until its final plunge. Phobos has grooves that may be signs of breaking apart. The surface of Phobos is marked by a distinctive pattern of linear grooves, and scientists have debated whether these features are signs of the Moon being slowly torn apart by Mars' tidal forces. Some of the grooves appear to radiate outward from the giant Stickney crater, suggesting they may be fractures caused by that ancient impact. However, other grooves do not align with Stickney and instead appear to follow stress patterns consistent with tidal deformation. Recent studies suggest the grooves may be stretch marks developing as Phobos is pulled apart. The grooves range from less than 100 meters to several hundred meters wide. If Phobos is indeed fragmenting, the process is still in its early stages, but will accelerate. These linear scars may be the first visible signs of a moon's impending destruction. Deimos orbits so smoothly it barely rises or sets. Mars' outer moon Deimos orbits at a distance of about 23,500 kilometers, completing one orbit every 30 hours in the same direction as Mars rotates, but only slightly faster. From the Martian surface, Deimos appears to move very slowly across the sky, taking about 2.5 Martian days to rise and set. Its motion is so leisurely that an observer would see Deimos change phases from new to full, during a single crossing of the sky. Deimos is even smaller than Phobos, measuring only about 12 kilometers across. Unlike Phobos, which is spiraling inward, Deimos is slowly moving outward from Mars. Deimos drifts serenely through the Martian sky, a patient companion to the doomed Phobos. Mars, moons may be captured asteroids. The small sizes, irregular shapes and dark surfaces of Phobos and Deimos have led scientists to suggest these moons are captured asteroids rather than bodies that formed alongside Mars. Their compositions appear similar to carbonaceous asteroids found in the outer asteroid belt. However, capturing an asteroid requires removing energy from its orbit, and the mechanisms for doing so remain debated. An alternative hypothesis suggests that Phobos and Deimos formed from debris thrown into Martian orbit by a giant impact. This impact origin would explain why the moons orbit close to Mars' equatorial plane. Recent spectroscopic studies have produced mixed results. The true origin of Mars' moons remains one of the outstanding mysteries of the inner solar system. Phobos will either crash into Mars or become a ring. The ultimate fate of Phobos depends on whether the moon survives long enough to cross Mars' Roche limit. If Phobos is relatively solid, it may survive until it actually strikes Mars, creating a significant impact. However, if Phobos is a loosely consolidated rubble pile, as some evidence suggests, it will likely be torn apart before reaching the surface, with debris spreading into a ring around Mars. This ring would be temporary on geological timescales, lasting perhaps only a few million years. Some scientists believe Mars may have experienced several cycles of moon formation and destruction throughout its history. Phobos' destiny as an impact or a ring represents two dramatically different endpoints. Charon is so large that Pluto and it spin around each other. With a diameter of about 1,212 kilometers, Charon is so large that the barycenter around which both bodies orbit lies in space between them rather than inside Pluto. This makes the Pluto-Charon system more of a double dwarf planet than a typical planet-moon pair. Charon's mass is roughly 1/8 of Pluto's, making it proportionally the largest moon relative to its primary in the solar system. Both objects complete one rotation and one orbit in about 6.4 Earth days, meaning the same hemispheres always face each other. From Pluto's near side, Charon hangs motionless in the sky, never rising or setting. Pluto and Charon dance through the outer solar system as partners, bound together by gravity. Charon has a canyon 4 times deeper than the Grand Canyon. The surface of Charon is dominated by an enormous canyon system named Serenity Chasma that stretches for over 1,600 kilometers across the Moon's equatorial region, reaching depths of up to 9 kilometers. This makes Serenity Chasma roughly 4 times deeper than Earth's Grand Canyon. Scientists believe this giant rift formed when Charon's interior partially froze and expanded, causing the outer crust to crack and separate. The freezing of Charon's potential early ocean would have increased the Moon's volume by several percent. Other smaller chasms also scar Charon's surface, all apparently resulting from the same global expansion event. Charon's Great Canyon is a frozen testament to the violent forces that shaped this distant world. Pluto and Charon are sometimes called a double dwarf planet system. The unusual size ratio between Pluto and Charon has led some scientists to argue that they should be classified as a binary dwarf planet system. Unlike Earth and its moon, where the barycenter lies within Earth, the Pluto-Charon barycenter lies in empty space between the two bodies. Charon is large enough that if it orbited the Sun independently, it might qualify as a dwarf planet. The formation of this pair likely involved a giant impact, similar to the one that created Earth's moon. 4 smaller moons orbit around the Pluto-Charon barycenter. The debate over classification highlights the challenges of categorizing the solar system's variety. Pluto and Charon together represent a unique type of planetary system. Charon's surface is scarred with enormous canyons and cliffs. Beyond the Great Serenity Chasma, Charon's surface displays complex geology with numerous smaller canyons, cliffs, and scarps. The terrain south of the main canyon system shows extensive faulting, while the northern hemisphere appears smoother, creating a marked geological dichotomy. A distinctive dark polar cap nicknamed Mordor covers Charon's north pole, composed of reddish organic molecules called tholins. This polar cap gives Charon a unique appearance, as if wearing a dark crown on its northern reaches. Mountains rise from Charon's plains, some surrounded by moats that may have formed when cryolavas erupted. Each cliff and canyon tells a story of the forces that shaped this distant world in the dim light of the outer solar system. Miranda looks like it was shattered and reassembled. Uranus, Moon Miranda, displays one of the most bizarre surfaces in the solar system, with dramatic variations in terrain that appear as if pieces from different worlds were randomly stitched together. The surface includes ancient, heavily cratered regions adjacent to smooth, younger terrain, enormous cliffs, and strange geometric patterns called coronae. For decades, scientists speculated that Miranda might have been shattered by a massive impact and reassembled from the fragments. More recent analyses suggest the bizarre terrain may result from internal geological processes, possibly including tidal heating. The Moon's coronae are particularly striking, consisting of concentric ridges and troughs forming rectangular or ovoid shapes. Miranda's chaotic landscape makes it one of the most geologically interesting moons in the outer solar system. Miranda's Verona Rupes is the tallest cliff in the solar system. Rising approximately 20 kilometers above the surrounding terrain, Verona Rupes on Miranda is the tallest known cliff in the entire solar system. This enormous cliff is part of the boundary of one of Miranda's coronae and represents the edge of an uplifted or tilted crustal block. Because Miranda's surface gravity is only about 1/8% of Earth's, a hypothetical fall from the edge would last approximately 12 minutes. The cliff face would pass by almost in slow motion, giving plenty of time to contemplate the alien landscape before eventual impact at about 60 kilometers per hour. Scientists believe Verona Rupes formed through extensional tectonics, where Miranda's crust was pulled apart. Verona Rupes stands as one of the most spectacular geological features ever photographed. Uranus, moons are named after Shakespeare's characters. Unlike other planetary moons typically named after figures from Greek and Roman mythology, the moons of Uranus are named after characters from Shakespeare and Alexander Pope. This tradition began when William Herschel discovered the first 2 Uranian moons and named them Oberon and Titania after the fairy king and queen from A Midsummer Night's Dream. Subsequent discoveries continued this literary theme, with moons named Ariel, Miranda, Puck, Juliet, Portia, Rosalind, and many others. The 5 major moons are Miranda, Ariel, Umbriel, Titania, and Oberon. The choice of Shakespearean names gives the Uranian satellite system a distinctive character. Each time a new moon is discovered, astronomers must search Shakespeare's works for suitable names. A fall from Verona Rupes would take 10 minutes to reach the bottom. The combination of Verona Rupes' extraordinary height and Miranda's very weak gravity creates a scenario where an object dropped from the cliff's edge would take approximately 10 to 12 minutes to reach the surface below. Miranda's surface gravity is only about 0.7 of a meter per second squared, meaning acceleration is dramatically slower. During this extended descent, a falling astronaut would have ample time to observe the cliff face passing by. The terminal velocity at the base would be only about 60 to 70 kilometers per hour. This thought experiment has captured public imagination since images of Verona Rupes were returned by Voyager 2. The slow fall from Verona Rupes remains one of the most compelling hypothetical adventures in solar system exploration. Some moons are shaped like potatoes or flying saucers. While large moons are pulled into spherical shapes by their own gravity, smaller moons often retain irregular forms that resemble potatoes, bones, or flying saucers. These irregular shapes occur when a body is small enough that its self-gravity cannot overcome the material strength of its rock and ice. Mars, moons, Phobos, and Deimos are classic examples of potato-shaped satellites. In the Saturn system, several small moons have developed distinctive flying saucer shapes with prominent equatorial ridges formed by accumulated ring particles. Atlas and Pan are perhaps the most striking examples. The diversity of moon shapes reflects the variety of formation mechanisms found throughout the solar system. Amalthea has valleys taller than Mount Everest. Jupiter's inner moon, Amalthea, is a small, irregularly shaped body, measuring roughly 260 by 140 kilometers, with surface relief so extreme that some features exceed the height of Mount Everest. The moon's largest crater, Pan, is over 100 kilometers across, nearly as large as the moon itself. Amalthea orbits deep within Jupiter's magnetosphere, constantly bombarded by high-energy particles that may be responsible for its distinctive dark red color. The moon's low density suggests it may be a loosely consolidated rubble pile. Amalthea was the last moon in the solar system discovered through direct visual observation rather than photography. Amalthea's extreme terrain demonstrates that even small moons can display dramatic geological features. Himalaya is one of Jupiter's strangest captured moons. Among Jupiter's irregular outer moons, Himalaya stands out as the largest, measuring about 170 kilometers in diameter and orbiting over 11 million kilometers from Jupiter. Himalaya belongs to a group of similarly inclined moons that all follow prograde orbits, suggesting they may share a common origin from the breakup of a larger captured body. These irregular moons were almost certainly captured from the asteroid belt or outer solar system, rather than forming alongside Jupiter. Himalaya's dark surface and spectral properties are consistent with carbonaceous asteroids. The moon was discovered in 1904, the first new moon found around Jupiter in nearly 300 years. Himalaya represents a piece of the early solar system that wandered into Jupiter's gravitational domain. Some moons are so small they are just giant space rocks. The outer planets possess dozens of tiny moons measuring only a few kilometers across, objects so small that they blur the line between moons and captured asteroids. Jupiter has over 90 known moons, Saturn has over 80, and most of these are tiny irregular bodies orbiting far from their parent planets. These small moons are assumed to be captured objects because their orbits are inconsistent with formation from the same disk that produced the large regular satellites. Many likely represent fragments of larger bodies that broke apart after capture. The smallest confirmed moons are only about 1 to 2 kilometers in diameter. The solar system's smallest moons are transitional objects, connecting the realm of satellites to the population of wandering small bodies. Some moons rival planets in size. The largest moons in the solar system approach or exceed the sizes of the smaller planets, challenging assumptions about what separates moons from planetary bodies. Ganymede and Titan are both larger than Mercury, while 4 other moons exceed the size of Pluto. If these giant moons orbited the Sun directly, they would qualify as dwarf planets, or perhaps full planets. Titan possesses a thicker atmosphere than Earth and maintains a complex weather system with rain, rivers and lakes. Europa and Enceladus, though much smaller, harbor subsurface oceans that may be habitable. The size overlap between large moons and small planets demonstrates that the distinction is largely historical and positional. Some of the most interesting worlds in our solar system are moons, not planets. Many moons are tidally locked to always show the same face. Just as our moon always presents the same face toward Earth, most large moons in the solar system are tidally locked to their parent planets. This tidal locking develops over time as gravitational friction within the moon dissipates rotational energy, eventually synchronizing the rotation period with the orbital period. The inner major moons of all the giant planets are tidally locked, as are both Martian moons and all the moons of Pluto. The process occurs faster for moons that orbit closer to their planets. Once locked, a moon remains in this configuration indefinitely. An observer on the planet-facing side of a tidally locked moon would see their parent planet hanging motionless in the sky. The near-universal tidal locking of major moons demonstrates the powerful influence planets exert on their companions. Some moons spin so slowly they barely rotate at all. While tidally locked moons rotate once per orbit, some of the solar system's smaller and more distant moons have rotations that are even slower. These slow rotations typically result from complex gravitational interactions with multiple bodies. Saturn's moon Hyperion is a famous example of the opposite extreme, tumbling chaotically with no predictable rotation at all. The irregular satellites of the giant planets often have rotation periods that differ significantly from their orbital periods, having never experienced tidal forces strong enough to lock them. Some asteroids that have been captured as moons retain the rotation rates they possessed as independent bodies. The slowest rotating objects can take Earth days or even weeks to complete one spin. Rotation rates among moons vary as widely as any other property. Some moons are locked in resonant orbits. Orbital resonances occur when two or more moons exert regular gravitational tugs on each other at the same points in their orbits, creating stable configurations that persist for billions of years. The most famous example is the Laplace resonance among Jupiter's moons, Io, Europa and Ganymede, where for every 4 orbits Io completes, Europa completes exactly 2, and Ganymede completes exactly 1. This precise relationship keeps the orbits slightly elliptical, maintaining the tidal heating that drives Io's volcanism. Saturn's moons Mimas and Tethys are locked in a 2-to-1 resonance, contributing to geological activity. Resonances can also protect moons from perturbations. The celestial clockwork of resonant moons demonstrates how gravity can create order from orbital dynamics. Janus and Epimetheus swap orbits around Saturn. Saturn's moons Janus and Epimetheus occupy nearly identical orbits separated by only about 50 kilometers, and every 4 years they actually exchange orbital positions in a cosmic dance unique to these two satellites. As the inner moon catches up to the outer moon, their mutual gravitational attraction gives the inner moon a boost and the outer moon a break, causing them to swap positions. This horseshoe orbit configuration allows both moons to avoid collision, despite their extreme proximity. After the swap, the process reverses over the next 4 years until they switch again. Janus is about 179 kilometers across, while Epimetheus measures about 116 kilometers. Janus and Epimetheus perform a gravitational pas de deux, unlike any other known configuration. Moons sometimes trade orbits with each other. Beyond the remarkable case of Janus and Epimetheus, several other moon pairs occupy orbital configurations where significant interactions can cause exchanges. Saturn hosts several sets of Trojan moons, where smaller satellites share orbits with larger ones at the gravitationally stable Lagrange points. Tethys has two small Trojan companions, Telesto and Calypso, while Dione has Hele and Polydeuces. These configurations are stable because the gravitational influence of the larger moon creates potential wells where smaller objects can remain trapped. In more extreme cases, moons on nearby orbits can gravitationally scatter each other, potentially exchanging angular momentum. Over billions of years, these interactions have shaped the current architecture of the satellite systems. Moons can be torn apart by planetary gravity at the Roche limit. Every planet has a distance known as the Roche limit, within which any substantial moon would be torn apart by tidal forces. The exact location depends on the densities of both the planet and the moon. Saturn's iconic rings exist almost entirely within the planet's Roche limit, which is why the ring material has never coalesced into a moon. Larger moons that spiral inward, like Triton and Phobos, will eventually cross their respective Roche limits and be shattered. Comets that pass too close to giant planets can also be destroyed, as happened to comet Shoemaker-Levy before it impacted Jupiter. The Roche limit represents the invisible boundary between survival and destruction for moons. Some moons could one day break apart into rings. As moons spiral toward their parent planets through tidal decay, several in our solar system are on trajectories that will eventually lead to destruction and potential ring formation. Phobos will be torn apart by Mars in approximately 50 million years, potentially creating a thin ring. Triton is spiraling toward Neptune even more slowly, destined to become a ring system in perhaps 3 to 4 billion years. These future rings would be temporary features, eventually dissipating through various processes. The life cycle of rings appears connected to the destruction and reformation of moons over billions of years. Some scientists believe Saturn's current ring system may have formed from a destroyed moon within the last few hundred million years. The eventual fate of doomed moons provides a window into the processes that create and destroy rings. Saturn's moons sculpt its rings into beautiful patterns. The intricate structure of Saturn's rings, with their sharp edges, gaps, waves, and braided features, is largely created by the gravitational influence of the planet's many moons. Moons orbiting within or near gaps act as shepherds, clearing corridors by scattering particles that stray too close. Pan creates the Encke gap, Daphnis creates the Keeler gap, and the sharp outer edge of the A-ring is maintained by the Moon Atlas. Gravitational resonances with larger, more distant moons like Mimas create waves visible as density variations in high-resolution images. The interplay between moons and rings is dynamic, with features evolving over millions of years. Saturn's rings are not static decorations, but active environments constantly shaped by lunar sculptors. Dust clouds from moons can form invisible rings. Beyond the bright, obvious rings of Saturn, dust ejected from moons creates faint, diffuse rings that are often invisible to the naked eye, but detectable by spacecraft. Jupiter's Gossamer rings are created by dust knocked off the small moons Amalthea and Thebe by micrometeorite impacts. Saturn's Phoebe ring is an enormous and extremely faint structure created by dust spiraling inward from the distant moon Thebe. These dust rings are maintained in a steady state, with material constantly being produced and lost. The particles are typically micrometer-sized, small enough to be significantly affected by non-gravitational forces. The invisible halo of dust surrounding planetary systems reveals ongoing processes of creation and destruction. Some moons formed from rings that collapsed. While rings are often thought of as the debris of destroyed moons, the process can also work in reverse, with ring material accumulating into new moons. Beyond the Roche limit, where tidal forces no longer prevent gravitational clumping, ring particles can gradually coalesce under their own gravity. Saturn's small inner moons, including Pan, Atlas, and ring-embedded moonlets, may have formed this way. This formation process explains the distinctive equatorial ridges seen on some of these moons. The cycle of moon destruction and ring formation may repeat over billions of years. Computer simulations suggest that rings naturally spawn moonlets near their outer edges. The satellite systems of giant planets may be more dynamic than we once imagined. Some moons are so dark, they reflect almost no light. Among the darkest objects in the solar system are small moons that reflect less than 5% of the sunlight that reaches them. Saturn's moon Phoebe has an albedo of only about 6%, while Iapetus, leading hemisphere, is even darker at around 4%. These dark surfaces typically result from coating by carbonaceous material and organic compounds that have been space-weathered into nearly black residues. Some dark material originates from impacts on other bodies, with dust spiraling inward and coating moons in its path. The irregular satellites of the giant planets are often quite dark, consistent with their presumed origin as captured bodies rich in dark organic matter. These shadow moons are absorbers of light, hidden in plain sight at the edges of their planetary systems. Other moons are so bright they glow like fresh snow. At the opposite extreme from dark moons, some satellites are so highly reflective that they bounce back nearly all the light that reaches them. Enceladus leads the pack with an albedo approaching 100%, reflecting essentially all sunlight due to its surface of pristine ice constantly renewed by geyser activity. This makes Enceladus the most reflective body in the entire solar system. Tethys and Dione are also remarkably bright, with albedos exceeding 60%. Europa reflects about 64% of incoming light. The brightness of these moons depends on both their surface composition and geological history. These bright moons stand out against the darkness of space, beacons of reflected sunlight in the outer solar system. Some moons glow with auroras of their own. Just as Earth experiences auroras when charged particles interact with our magnetic field and atmosphere, several moons display their own versions of these light shows. Ganymede produces auroras as Jupiter's magnetospheric particles collide with its thin oxygen atmosphere. Europa also shows faint auroral emissions, produced when electrons bombard water molecules sputtered from its surface. Io's volcanoes inject material into Jupiter's magnetosphere, creating an auroral glow. These moon auroras differ from Earth's because the moons lack global magnetic fields capable of channeling particles toward polar regions. The auroral glow provides valuable information about the composition of thin atmospheres. Auroras on moons are silent light shows witnessed only by spacecraft. Some moons glow bright enough to cast shadows. The largest and most reflective moons can appear bright enough in the night sky of their parent planets to cast visible shadows, much as our moon illuminates Earth's landscape during full moon nights. From Jupiter's atmosphere, Ganymede would appear about as large as our moon from Earth, and could rival its brightness. Titan, despite its orange haze, would still appear substantially larger than any moon seen from Earth if viewed from within Saturn's atmosphere. Europa's highly reflective surface would make it a brilliant beacon in Jupiter's sky. The ability to cast shadows depends on both a moon's intrinsic brightness and its angular size. The moonlit nights of the outer planets are far more complex than our own, with multiple moons creating overlapping zones of light and shadow. Some moons hide subsurface oceans warmed by tidal heating. The discovery that several moons contain liquid water oceans beneath their icy surfaces has revolutionized our understanding of habitability. Europa, Enceladus, and likely Ganymede and Callisto all possess subsurface oceans maintained by tidal heating. This heating occurs when a moon's orbit is slightly elliptical, causing tidal forces to strengthen and weaken cyclically. The resulting friction generates enough heat to maintain liquid water far beyond the conventional habitable zone. Io represents the extreme case where tidal heating is so intense that the interior is largely molten. For ocean moons, the heating is gentler, just enough to maintain liquid water where conditions might support life. Some moons may harbor prebiotic chemistry beneath their surfaces. The conditions within subsurface oceans of moons like Europa and Enceladus may support the kind of complex organic chemistry that preceded life on Earth. These oceans have been in contact with rocky interiors for billions of years, potentially leaching minerals that could facilitate complex molecule assembly. Energy sources including hydrothermal venting and radiation-driven chemistry could drive reactions toward increasing complexity. Organic molecules delivered by comets over billions of years would provide the raw materials, including amino acids and nucleotides. Laboratory experiments simulating ocean-moon conditions have produced complex organic compounds. The outer solar system may contain multiple independent experiments in prebiotic chemistry. Moons may contain hydrothermal vents, like Earth's oceans. Evidence from the Cassini mission suggests that hydrothermal activity is occurring on the sea floor of Enceladus, and similar processes likely operate in other ocean moons. The detection of silica nanoparticles and molecular hydrogen in Enceladus plumes strongly indicates hot water interacting with rock at the ocean floor. On Earth, hydrothermal vents support thriving ecosystems that derive energy from chemical reactions rather than sunlight. The conditions at hydrothermal vents are considered plausible settings for the origin of life itself. If hydrothermal vents exist on ocean moons, they may provide habitats where microbial life could thrive. The sea floors of distant moons may harbor oases of warmth and chemistry. Life could potentially emerge on moons, not just planets. The traditional view that life requires planets orbiting within habitable zones has been challenged by the discovery of ocean moons in the outer solar system. These moons demonstrate that tidal heating can maintain liquid water far beyond conventional habitable zones. If life exists on Europa, Enceladus, or another ocean moon, it would prove that planets in stellar habitable zones are not the only places where biology can arise. This realization has profound implications for the search for life in other star systems. The conditions on ocean moons match what we believe are the minimal requirements for life. The quiet moons of the outer solar system may prove to be the most biologically interesting worlds orbiting our Sun. Moons can create their own mini-magnetospheres. When a moon possesses its own intrinsic magnetic field, it can carve out a protected region within its parent planet's larger magnetosphere. Ganymede is the only moon known to generate its own magnetic field through internal dynamo action. This intrinsic field interacts with Jupiter's much larger magnetosphere to create a miniature magnetosphere around Ganymede. Even moons without internal dynamos can create induced magnetospheres if they contain electrically conducting layers like salty oceans. Jupiter's rotating magnetic field induces electrical currents in these layers, generating secondary magnetic fields. The magnetic interactions between moons and their parent planets provide valuable tools for probing hidden interiors. Galileo's discovery of moons proved Earth is not the center. When Galileo Galilei turned his telescope toward Jupiter in 1610 and observed 4 bright points orbiting the planet, he provided the first direct evidence that not everything revolves around Earth. These 4 moons clearly orbited Jupiter, demonstrating that celestial bodies could orbit centers other than our planet. This observation was crucial evidence supporting the Copernican model. The Catholic Church initially opposed these findings, but the evidence became impossible to ignore. The Galilean moons proved that the universe was far larger and more complex than previously imagined. 4 points of light seen through an early telescope changed humanity's view of the universe forever. Moons are key to understanding how planets form. The satellite systems of giant planets preserve valuable information about conditions in the early solar system. Regular moons, like the Galilean satellites, likely formed in miniature disks of material orbiting their parent planets, mirroring the processes that built the planets themselves. The compositions and orbital properties of moons reflect the temperature and conditions when they formed billions of years ago. Studying the gradation among the Galilean moons reveals how ice content varied with distance from the warm, young Jupiter. Irregular moons in distant, inclined orbits record the capture of stray bodies from the broader solar system. Every moon system is a frozen record of the chaotic processes that shaped the solar system architecture. Some moons are so young they are still forming. While most moons formed billions of years ago, some satellites may be geologically young or actively in the process of accreting material today. Saturn's inner moons embedded within or near the ring system appear to have accumulated their equatorial ridges relatively recently. Some small moons may have formed from ring material within the last few 100 million years. The ring moon system of Saturn appears to be dynamically active, with material cycling between rings and moonlets over timescales much shorter than the age of the solar system. Moonlets within the rings are constantly bombarded by material that alternately adds to their mass or chips pieces away. The satellite systems of giant planets may be more dynamic than we once imagined. Moons may shatter and reform after catastrophic collisions. The violent history of the solar system included countless collisions between moons and smaller objects, some powerful enough to completely shatter satellites into clouds of debris that later reaccumulated under gravity. Miranda's bizarre patchwork surface was once interpreted as evidence of shatter and reassembly. Other moons may genuinely preserve evidence of catastrophic disruption, particularly among the irregular satellites. The inner moons of Uranus show signs of a complex collisional history. Computer simulations suggest that violent collisions can eject material into temporary debris rings that gradually coalesce into new moons. The moons we see today may be phoenix-like survivors, risen from the debris of earlier generations destroyed by ancient impacts. Moons can be swallowed when planets migrate. During the early history of the solar system, giant planets likely migrated significant distances from their formation locations, with dramatic consequences for any moons caught in their gravitational influence. As a planet migrates, its hill sphere changes in size and location, potentially destabilizing existing moons or capturing new ones. A planet migrating inward would experience a shrinking hill sphere, possibly stripping away outer moons. The NICE model suggests that the giant planets underwent significant migration, which could explain Neptune's unusual moon system, including the likely captured Triton. Migration-induced chaos may have destroyed many primordial moons. The current architectures likely reflect both original formation conditions and subsequent migrations. Some moons orbit backwards compared to their planets. Retrograde moons that orbit in the opposite direction from their planet's rotation are strong evidence of capture rather than in situ formation. Triton is the largest and most famous retrograde moon, almost certainly a captured Kuiper Belt object. Many of the outer irregular satellites of Jupiter and Saturn also follow retrograde orbits, forming distinct dynamical groups from breakup of captured parent bodies. The capture of an object into a retrograde orbit requires some mechanism to remove energy, such as interaction with a primordial gas disk or collision with an existing moon. Once captured into retrograde orbits, these moons are generally stable. Retrograde moons provide windows into the population of small bodies that roamed the early solar system. Distant moons may be captured objects from the Kuiper Belt. Beyond the inner regular satellites of giant planets, swarms of small, irregular moons follow distant, inclined, and often retrograde orbits, indicating they were captured from the outer solar system. These irregular satellites share characteristics with Kuiper Belt objects and centaurs. The capture mechanism likely involved gas disks that surrounded young giant planets, providing drag to slow incoming objects. Some irregular satellites may have been captured as binary pairs. The compositions of these distant moons appear consistent with primitive outer solar system material. Studying these captured objects provides information about the small body population from billions of years ago. The irregular satellites are immigrants from the cold outer reaches. Neptune's moons were likely captured from elsewhere. Neptune's satellite system is dramatically different from those of other giant planets, dominated by a single large retrograde moon, Triton, surrounded by a handful of small irregular objects. This unusual configuration suggests that Neptune's original moon system was destroyed when Triton was captured. Triton's retrograde orbit is slowly decaying, indicating tidal friction is transferring its orbital energy to Neptune. The few small moons that currently orbit Neptune include some that may be debris from the original system. The entire Neptunian system appears to be a record of violent capture and subsequent rearrangement. Neptune's moons tell the story of a cosmic kidnapping that reshaped an entire satellite system. Some moons orbit so far they are nearly independent worlds. The outermost irregular satellites of giant planets orbit at such extreme distances that they take years or decades to complete a single circuit, spending most of their time where the Sun's influence nearly rivals that of the planet. Saturn's moon Phaunchot orbits at about 25 million kilometers, completing one orbit every 3.5 years. These distant satellites follow complex, unstable orbits that can be perturbed by passing objects and the Sun's interference. Despite their great distances, these moons remain gravitationally bound because they orbit within the planet's Hill sphere. These far-flung satellites represent the outer limit of what can meaningfully be called a moon. Other moons skim so close they almost touch their planets. At the opposite extreme from distant irregular satellites, some moons orbit so close to their parent planets that they complete multiple circuits per planetary day. Metis, Jupiter's innermost known moon, orbits at only 128,000 kilometers from Jupiter's center, completing one orbit in less than 7 hours. At this proximity, tidal forces are intense. Phobos orbits Mars at only about 6,000 kilometers above the Martian surface. Saturn's Pan orbits within the Encke Gap, actually embedded within the Ring system. These close-orbiting moons experience intense radiation environments and complex gravitational interactions. Moons may carry traces of comets that struck them. Over billions of years, moons throughout the solar system have been bombarded by comets and asteroids, with each impact delivering material from the broader solar system. These impacts leave behind not just craters but also chemical traces of the impacting bodies, including water, organic compounds, and other volatiles. The water ice found on our Moon's polar regions may have been delivered by comet impacts. Similarly, the surfaces of outer solar system moons bear the chemical fingerprints of countless visitors. The organic compounds detected in some moon surfaces may be a mixture of in situ material and imported chemistry. Every large crater on a moon represents both a physical scar and a potential deposit of alien chemistry. Some moons leak atmospheres into space. Several moons in the solar system possess thin atmospheres that are continuously escaping into space, requiring ongoing replenishment to maintain even their tenuous presence. Io's atmosphere of sulfur dioxide is constantly being stripped away by Jupiter's radiation, replaced by fresh volcanic outgassing. Titan's much thicker atmosphere is slowly leaking methane and nitrogen into space. On Enceladus, the geyser activity that creates the E-ring is literally the Moon's interior escaping into space. Europa and Ganymede also lose oxygen and hydrogen from their thin atmospheres. These atmospheric losses mean that Moon atmospheres are dynamic systems requiring continuous regeneration. The thin veils of gas surrounding these worlds are evidence of ongoing processes. Moons have been found orbiting dwarf planets beyond Pluto. The discovery of moons around distant dwarf planets has revealed that satellite systems are common throughout the outer solar system. Pluto's system of 5 moons, with Charon being nearly half Pluto's size, was the first documented in detail. Many other trans-Neptunian objects also possess companions. The presence of moons around dwarf planets provides crucial information about the masses of these distant objects. Without their moons, determining the masses of these faint objects would be extremely difficult. These discoveries also suggest that binary systems may be common in the distant trans-Neptunian region. The cold frontier beyond Neptune is populated by dwarf planets with their own miniature satellite systems. Eris and Haumea have their own moons. Beyond Pluto, the dwarf planets Eris and Haumea both possess satellites that reveal information about these distant worlds. Eris has a moon named Dysnomia that orbits with a period of about 16 days. By tracking Dysnomia's orbit, astronomers determined that Eris is about 27% more massive than Pluto, despite being roughly the same size. Haumea has 2 small moons named Hiaka and Namaka that appear to be fragments from an ancient collision. The discovery of moons around these distant dwarf planets supports the idea that collisions in the early trans-Neptunian region were common. Each newly discovered moon adds to our understanding of the cold, distant reaches beyond the major planets. Moons may outnumber planets by the thousands. In our solar system alone, the number of known moons vastly exceeds the number of planets, with Jupiter and Saturn, each possessing over 80 confirmed satellites. New moons continue to be discovered as telescope technology improves. Many additional tiny moonlets likely exist, but remain below the detection threshold. If small moonlets hidden within ring systems are included, the number could be higher still. Extrapolating to other star systems, moons may vastly outnumber planets across the galaxy. The universe may be filled with more moons than planets, more satellites than the worlds they orbit. Some moons orbit in clusters like miniature solar systems. The satellite systems of giant planets can be thought of as miniature solar systems in their own right, with large regular moons orbiting in the same direction as the planet's rotation. Jupiter's 4 Galilean moons form a system remarkably analogous to the inner solar system, with rocky Io closest in, followed by the icy potentially habitable Europa and Ganymede, And finally, ancient Callisto. The formation of these regular satellite systems in circumplanetary disks mirrored the formation of planets around the young Sun. Saturn's system is even more complex, with diverse mid-sized icy moons and the unique Titan. These miniature planetary systems offer accessible laboratories for testing theories of planet formation. Moons could serve as refuges for future space colonies. As humanity looks toward expanding beyond Earth, moons throughout the solar system offer potentially valuable sites for future settlement. Saturn's moon Titan has been proposed as a particularly interesting destination because its thick atmosphere provides protection from radiation. Jupiter's moon Callisto orbits far enough from Jupiter to avoid the worst radiation belts while providing access to water ice. Our own moon is the most accessible destination for near-term settlement, with water ice in polar craters. The subsurface oceans of Europa and Enceladus would be extremely difficult to access. Moons of Mars, particularly Phobos, have been suggested as staging points for Mars surface operations. The moons of our solar system may one day serve as stepping stones for human expansion. Some moons are slowly spiraling into their planets. While most moons that formed alongside their planets have been spiraling slowly outward due to tidal energy transfer, some are on opposite trajectories toward eventual destruction. Phobos is the most famous example, losing orbital energy through tidal interactions and approaching Mars by about 1.8 centimeters per year. Triton's retrograde orbit around Neptune also leads to inward spiraling. Some close-orbiting moons may be in quasi-stable configurations that could become unstable. The process of tidal spiraling is usually slow, taking millions to billions of years. The eventual fates of these doomed moons will reshape their planetary systems dramatically. Exomoons could be even stranger than the ones we know. Beyond our solar system, exomoons orbiting planets around other stars could display far greater variety than the satellites we observe in our own neighborhood. Giant exoplanets in habitable zones could host Earth-sized moons with atmospheres, oceans, and potentially life. Some exomoons might be larger than their host planets, if the planets are relatively small. The detection of exomoons remains extremely challenging because the subtle effects they produce are difficult to distinguish from noise. Nevertheless, several candidate exomoons have been proposed based on transit data. If confirmed, these exomoons would provide valuable comparisons to our own solar system satellites. The universe may contain moons of types we cannot yet imagine. The origins of many moons are still unsolved mysteries. Despite decades of study, the formation and evolution of many solar system moons remain poorly understood. The origin of Mars, moons Phobos and Deimos is still debated, with evidence supporting both the captured asteroid and giant impact hypotheses. Triton's capture by Neptune is widely accepted, but the mechanism remains speculative. The unusual properties of Uranus' moon system hint at a violent history not fully reconstructed. Even our own moon's formation through giant impact still has details that are actively debated. The thermal and chemical evolution of ocean moons depends on parameters we cannot directly measure. Each moon holds secrets about its past that future missions may one day reveal. Moons remind us that planets rarely travel alone. From tiny potato-shaped asteroids orbiting Mars to giant world-sized satellites orbiting Jupiter, moons demonstrate that companionship is the norm rather than the exception. Every giant planet possesses dozens of moons, and even dwarf planet Pluto has 5 known satellites. Moons shape their planets through tidal forces, stabilize planetary axes, create rings, and may harbor conditions that could support life. They record the history of the solar system in their craters and preserve ancient oceans beneath icy crusts. The diversity of moons suggests that satellites may be common companions to planets throughout the galaxy. In the vast dark of space, planets and their moons travel together, partners in the endless dance of gravity and time. And now the quiet wonders of moons begin to gently fade into the stillness of the night. You have wandered through over 100 peaceful truths. From our own moon with its silent footprints and ancient craters, to the icy oceans of Europa, the fiery volcanoes of Io, and the frozen geysers of Enceladus. You have explored the hidden rhythms of tidal forces, the slow dance of moons locked in orbital resonance, and the strange companions that orbit in every corner of our solar system. You are part of this story. Not just an observer, but the story itself. Every atom in your body was forged in stars that once shone upon ancient moons. The iron in your blood, the oxygen you breathe, the carbon in your bones, all of it was born in stellar furnaces and scattered across cosmic distances. If your eyes feel heavy now, let them close. Let the rhythm of your breath become steady, like the gentle orbit of moons around their planets, like the patient drift of satellites through the cosmic dark. Tonight, as you rest, moons continue their ancient motion. Geysers are erupting on Enceladus. Volcanoes are glowing on Io. Somewhere beneath Europa's ice, an ocean waits in silence. You are a small, warm presence within this vast solar system, peacefully resting among the wonders of existence. Sleep well. Sweet dreams. And may you carry with you the quiet knowledge that you are woven into something vast and beautiful. A universe of countless moons, each one a story written in craters and ice. Thank you for joining me on this journey through the wonders of moons. If you enjoyed this video, please subscribe to Drowsy Discovery for more soothing explorations of science and our remarkable universe. There are more wonders waiting. More secrets hidden beneath icy crusts. More mysteries to drift through on quiet evenings. Rest well. And may the moons keep you company through the night. This has been Drowsy Discovery. Good night.